take one of trying to understand string theory on AdS3 cross S3 cross T4. With the idea of showing that this is the same as this, that string theory in that background is the same as the symmetric orbifold. And what we've been concentrating on is the description of this factor. That factor and that factor are pretty standard. There's nothing specific happening here. And here I propose we should describe this in terms of an SL2R Wessel-Minowitten model. And we're going to set k equals to 1 shortly. And what I argued was that a Hilbert space, or well, it's not Hilbert space because this is a non-unitary theory, so the space of states of this Wessel-Minowitten model. And I should say that first of all this is take one, and secondly we are just following Maldacino-Oguri here. So this is not our work, but I think this is a very well-defined, well-motivated proposal, is that the space of states has the form that you sum over the spectral flow, and actually we're going to sum over all non-negative integers, and then we have a sum, or as Giovanni pointed out, it's really a direct integral of representations of the SL2R affine Kac-Moody algebra, and then we have sigma W of Hj for the left movers, and sigma W of Hj for the right movers. So this is the highest rate representation labeled by J, and sigma of W is the spectral flow automorphism that induces this non-highest rate representation from the highest rate representation. And as I said last time, here we should sum over the discrete, a certain set of discrete representations. So only you get a certain set of discrete representations because of the no-ghost theorem. So you have to demand that after imposing the physical state condition, you should have a positive definite spectrum, so that forces the spin of the discrete representations to lie in this window. And then you have the continuous representations. They are of the form that the spin is of the form a half plus IS, where S is a real number. And as I said, this is take one. So we are going to go look at k equals to 1. And for reasons that are not particularly well motivated in this context, we are only going to look at the continuous representations. Yes?
How do you find the physical subspace?
I'll explain that very shortly. Okay. That's what I'm going to explain to you. Mm-hmm. And for the moment, we just want to concentrate on that. And at this stage, there's no good reason why we shouldn't look at the discrete representations, but let's just follow me and just look at this stuff. And in take two, we'll reformulate this in terms of a representation theory of the PSU 1,1/2 Wessel-Minowitten model. And then we'll see that these are in fact the only allowed representations at k equals to 1. But here, this is not so obvious. And the reason is that, as I mentioned, this factor at k equals to 1 is a bit delicate, so this is a bit more subtle. So this is really take one. So what do we have to do? So this is the spectrum of your CFT, and now you have to find the physical states of string theory. So what are the physical states of string theory? You have to look at the full space of states of all the three factors, the full spiel, and then you have to look at the states that are annihilated by the positive Virasoro modes and the positive n equals to 1 superconformal modes. So this is the Virasoro algebra, and it's the total Virasoro algebra with c equals to 15. This is, I haven't explained this to you in detail, there's actually an n equals to 1 superconformal algebra on the worldsheet, not just a conformal algebra, because we are doing superstring theory, and therefore you also have to impose that the positive supercharge, these are the supercharge of the n equals to 1 superconformal algebra annihilated, but ignore this. I mean, this is, I can't explain all the details. This is a side issue. This is not that important. So this is what you have to impose. And on top of you have to impose the mass shell condition. And the mass shell condition tells you that L0 on phi is equal to a half times phi. And what I'm doing here is I'm looking only at the Nervius-Schwarz sector on the worldsheet. There's a similar story for the Raman sector, i.e. when the fermions are integer moded. But again, for the sake of simplicity, let me just look at the Nervius-Schwarz sector. It already shows you all that you really want. Yes.
So this condition, you impose them for only one state or for a set of states?
No, so what the idea is you look inside the full space of states. Okay. You look at the subspace of states that satisfy this condition. And that subspace of states you should think of as being the physical degrees of freedom of string theory. This is removing the gauge degrees of freedom from the fact that the worldsheet you can reparameterize, and that is not physical, so this is a gauge degree of freedom, this is a gauge fixing condition, and you're choosing the physical states, and these physical states you want to identify with the states of space, of the space of states of the dual CFT. So this is going to be the infinite dimensional vector space of states that will satisfy this condition. Now, what's important is we're going to look at the continuous representations, and spectral flow will play an important role. So let me remind you how spectral flow acts on at least two of the generators, and that will be important. So remember, on the J3n generator, spectral flow acts as J3n plus k w over 2 delta n comma 0. And then on the Virasoro algebra, it acts as ln minus w j3n minus k over 4 w squared delta n comma 0. I mean, I'm not writing out the full spectral flow action, but these are the two pieces I will need.
The L's were quadratic in J's or something? Or what was it?
Well, the L's are the Virasoro generators, so they're quadratic in the J's. And then from the normal ordering piece, you pick up this piece, and then there's a normal ordering term. And it's fixed by the self-consistency of the automorphism. I mean, you can fix this term simply by demanding that that's an automorphism of the SL2R level K theory, affine Kac-Moody algebra, together with the Virasoro algebra that you can adjoin to it by virtue of the Shugawara construction. Okay, so this is in principle now a totally well-defined problem, right? So you know what the space of states is. Inside the space of states, you have to solve these conditions. And now you're just going to enumerate all the states that satisfy. Now, obviously, there are going to be infinitely many states. So the answer will be infinite. So you have to sort of organize a little bit the states you're going to get. Now, how do you want to organize them? Well, you would like to organize them so you recognize what the dual 2D CFT is. So how do you organize the states in a two-dimensional conformal field theory? Well, you organize them by keeping track of the conformal dimension of the individual states. So we would like to organize the physical spectrum by keeping track of the conformal dimension of the dual CFT. So what is the conformal dimension of the dual CFT? And this is sometimes called L0 spacetime. Now this is not to be confused with this L0. This is the L0 on the worldsheet. But what is the charge of the conformal dimension from the point of view of the dual CFT? And for that you have to think, so what is SL2R? So AdS3. AdS3 is a cylinder, topologically. The boundary is the surface of a cylinder. And if you add in infinity and minus infinity, it's a sphere. So the global symmetries of that will be the Möbius group. So the Möbius group of the dual CFT you want to identify with data I've described in terms of our worldsheet description. And if you think about it, the automorphism of SL2R are going to rotate the boundary, and therefore the generators of the space of the Möbius group of the spacetime CFT can be identified with the zero modes on the SL2R affine Kac-Moody algebra. So you will have that the spacetime plus one mode, so the minus one mode will be J plus 0, and the plus one mode will be J minus 0. So this is the dictionary for how you interpret the charges of the dual CFT from the point of view of your worldsheet description. I mean, this is very important.
What do you mean by dual CFT?
Well, so the idea is that this is dual to a 2D CFT, right? So what we are trying to see is that this is dual to a 2D CFT. And the picture is that this dual CFT lives on the boundary of AdS3. So you want to organize the physical states of this string theory in terms of conformal dimensions of this dual CFT. So you have to know what's the scaling dimension operator of the dual CFT from the point of view of this bulk description. And the obvious idea is that this is the correct description of the, so these are the Möbius generators.
I think that's how this word dual Isn't it somewhat misleading? Dual, you mean equal?
Well, so what I call dual CFT is the 2D CFT that's on the right-hand side. Whether you want to call it dual CFT or whatever you want to call it, it's the degrees. So what's the picture? I mean, you have string theory in AdS3, and you're asking what are the physical states, and the claim is the physical states look like the physical states of a 2D CFT that lives on the boundary of AdS3. And what I'm asking is what's the Möbius group of that CFT? And what I'm saying, the Möbius generators of that CFT are really just the global SL2R on the worldsheet. That's the SL2R is the global automorphism on the AdS3, and that's going to rotate the boundary, and therefore the zero modes, which are the global generators, are to be identified with the Möbius generators of the CFT that I'm about to identify. Yes.
If the boundary of AdS3 is two-dimensional, but we still have to multiply by the seven-dimensional thing, so why it's not a nine-dimensional CFT?
Well, so you think of it in terms of, so the additional degrees of freedom will be describing all the excitations of this 2D CFT. So you think of this as living on the boundary, and then all the degrees of freedom we come from S3 equals T4 will be what you think of as being the excitation degrees of freedom of this 2D CFT. Right. So I mean, think of it. Think of it as being the ant that lives on the boundary of AdS3. And you ask what are the physical states for the person who lives on the boundary of AdS3. The claim is from the point of view of the boundary of AdS3, it looks like a conformal field theory, and all the physical excitations of string theory will be whatever the excitations of this 2D CFT will be. That's the picture. So that's important. So what we're going to do is we're going to look at the physical spectrum, but we're going to keep track of the J30 eigenvalue, because that tells you what's the conformal dimension from the point of view of the dual CFT. So effectively what we're going to do is calculate the partition function of the, what I call the dual CFT. Anton objects is the 2D CFT living on the boundary of AdS3. We are asking if I think of all the physical states in AdS3 cos S3 cos T4, and I'm looking it through the lens of the person living on the boundary, what spectrum of L0 eigenvalues do I see? What's the multiplicity with which the state with L0 equals to whatever number will appear? And that I would then identify with the partition function of the 2D CFT that I postulate is equivalent to string theory on AdS3 cos S3 cos T4. That's the picture.
So this is a SL2R, so it means that, so these are self-adjoint, these two operators, or is it?
This is, no, I should have shown you this appendix, so you're asking me all nasty questions. So this is, I mean, this is on this level, this is just the Lie algebra. So so it is true, you see, I mean, these are Hermitian conjugates to one another, just like L minus 1 and L plus 1. So the.
But I thought in SL2R they should be, each of them should be self-adjoint, right? Because it's 0, 1, 0, I don't know.
Well.
So you complexify it, right?
Yeah, but anyway, so I mean, when you do the SL2R by Sumino-Witten model, the adjoint operator maps plus to minus, just it maps L minus 1 to L plus 1 in Virasoro.
And then you also have L0 bar and so on.
Well, so absolutely. I'm looking just at the left movers. But obviously, you see, everything I have to do, I also have to do for the right movers. And I'm just going to look at the left movers, and then I have to worry about how the left movers and the right movers get coupled together. And it's a good point, I should mention how this works, but for the moment I'm just looking at the left mover. Okay. Yes.
I'm a little confused about the superscript. So ST
Yes.
doesn't mean is the Virasoro on the worldsheet string theory. It means it's the Virasoro of the boundary?
Yes, yes. So ST stands for space-time.
Okay.
I mean,
not string theory.
Not string theory,
Okay,
sorry.
good.
I mean, so it's the CFT on the right-hand side.
Okay.
Right. Whether you call it space-time CFT or dual CFT or whatever you want to call it, it's that CFT and it's not this CFT. This Virasoro algebra is the conformal transformations on the worldsheet. The other one is the conformal transformations on the boundary sphere. And I can only identify simply the Möbius generators, the global symmetries, the local. I mean, this is going to be part of a Virasoro algebra. But the Virasoro generators I can't easily identify on the worldsheet. I can only identify the global bit, which is the Möbius group. Okay, so now.
And so we forgot about the other one, the SU2.
Right, so exactly. Well, so I mean, I have to impose this condition for the full this condition I have to apply for the full Virasoro algebra, but as you'll see, the rest will just go along for the ride at this stage. So you'll see this, I'll mention it, I'm about to mention how this goes. Okay, so now I'm going to be a little bit, so these conditions, you know what these conditions morally do. These conditions will just kill 2 bosonic excitations and 2 fermionic excitations. That's what always happens in critical string theory. Because we are at c equals to 15, and this condition will restrict to 1, will reduce the number of oscillators by 1, but then at c equals to 15 there's another set of oscillators that are spurious. So these conditions will basically remove 2 sets of bosonic and 2 sets of fermionic excitations. And I'm not going to deal with that any further. So this, I'll just have to keep track of what all my excitations are, and then I'm going to remove 2 bosonic ones and 2 fermionic ones. That's what the Virasoro condition always does. So the interesting condition to look at is this condition. It's the mass shell condition. So what does the mass shell condition look like? And remember, we're going to look at the continuous representations only, for reasons I haven't really explained, but I hope you just go along with it. Okay, so what does it mean to demand that L0 is equal to a half? Okay, so what does this mean? So I'm going to, because I'm applying it in the spectrally flowed sector, L0 really acts like such. So what is this condition? This condition is L0. So L0 is a half plus, so I have to do this is J. So the Casimir associated to it is a quarter plus S squared. Then I have to divide this by K at level K. That's the contribution from the ground state of SL2R. Then I have some excitations, and the excitations I'm going to lump into just some excitation number n, and this excitation number n, in response to this question, is not just necessarily only the excitation number from SL2R, these are the excitation number of everybody. Right? So you have SU2, you have T4, so you're looking at a state, you're looking at the ground state conformal dimension plus excitation, so the L0 eigenvalue is the ground state conformal dimension plus the excitation number plus H rest, which is the conformal dimension of the ground state coming from SL2, SU2. So this is where the SU2 ground state and the T4 ground state sits. This is where all excitation sits. And that's the conformal dimension coming from the ground state of the SL2R factor, right? I mean, L0 is L0 plus L0 plus L0, L0 for SL2R plus L0 for SU2 plus L0 for T4. This accounts for SU2 and T4. This accounts for the ground state from SL2 plus all the excitations, including those from SL2. Okay, but now I have these additional terms. So I have this equation minus W, and this number I'm just going to call M. So M is the eigenvalue of J30 of the state I'm looking at. And then I have to subtract minus K over 4 W squared plus all of that, and that must be equal to a half. That's the mass shell condition. Right? That's the mass shell condition for the states that come from the continuous representation of SL2R.
There's no prefect in front of n.
No, I mean n is the excitation. I mean you know L0. I mean if you have an excitation number, the L0 just gets increased by the mode number of. So for example, if I have the state J3 minus 1 on some ground state, then L0 of this is the L0 of the ground state plus 1, right? And you just get the excitation number from here. So all the excitation numbers are lumped into here. So this can be SL2R, this can be SU2 excitation, T4. They all produce integers or half integers. I mean, it's all the fermions and the bosons. This is the ground state from SL2. That's the ground state from the rest. And this is the piece that comes from spectral flow. So that's the equation I have to solve, right? Now, what's nice about a continuous representation is that that equation I can solve very easily, because you see, this is really an equation for M. You see, unlike the why is this different for the discrete and the continuous representation? You know, in the discrete representation, the M eigenvalue and the J eigenvalue must differ by an integer, because remember, I mean, the M's are obtained by lowering from the J, and then the Casimir depends on J, and M depends on some some integrality condition relative to J. So this becomes a very complicated equation to solve for the discrete representations. But for the continuous representations, effectively trivial to solve. You can just solve this for M. So what do? You solve this for M. Okay, let's try to solve it for M. What is it? It's 1 over W. Right, so you bring this to the other side. And then you move everything here. So you get minus. So now, okay, let's set K equals to 1. So then I can ignore this K, and I can ignore this K. So they're all equal to 1. And now I'm solving this, so what do I get? I get minus a quarter plus s squared. So this is the quarter minus the half. And then I have minus w squared. And then I have plus n.
W squared divided by 4.
Right. Thank you. So that's what I get from simply solving this equation, right? And in the continuous representation, M runs over whatever it runs, so there'll always be a solution. Okay, so that's M. But remember, we want to organize our spectrum in terms of this quantum number.
So that doesn't need to be an integer?
No. In the continuous representation, remember, J, the states are labeled by J. J is a half plus IS, and M is of the form an integer plus any fractional part. And this fractional part, so the only thing, and that'll come back to what Giovanni is asking, the only thing you have to insist on that the fractional part for the left movers and the right movers is the same. That'll be how the left and right movers get glued together. But individually, it's arbitrary. So alpha runs over all possible values between 0 and 1. So there'll always be a solution, and that'll tell you which value of alpha.
Alpha is a parameter of the representation.
Yes, exactly. So this integral here includes the integral over S, but it also includes the integral over alpha from 0 to 1.
Sorry, but what is given and what is looked for here? So you give the, I thought you give the representation, then you should also give alpha, right? You give W.
So what I'm thinking of, I look at some arbitrary excitation state,
Yes.
and I'm fixing the excitation, but I'm keeping the labels J and M variable. Right? So in every SL2R representation, there is a corresponding state. And I'm solving for M. Well, actually, I'm going to set S equal to 0 in a second, so I'm not actually varying J. I'm just keeping J fixed. I'm just looking for which value of alpha does the specific excitation of my ground state become physical.
And W, right?
Say again?
And W also is there.
Yes, for fixed W, I'm asking, so I'm looking at a specific state, sigma of W with some excitation number on some ground state. And I'm keeping sort of the alpha parameter here fixed, arbitrary. I'm fixing a specific excitation, and I'm asking when does this state become physical. And I'm saying it becomes physical provided that the M eigenvalue of this state is given by this formula, and that fixes from which alpha sector it comes. Okay. Now M isn't quite what we want, but it's almost what we want. Because remember, we want to organize the spectrum in terms of the eigenvalues of the scaling operator of the 2D CFT that's living in the space-time. Now that isn't quite J3, because you see in the W spectrally flowed sector, the real eigenvalue is shifted up by kW over 2. So H space-time, the space-time conformal dimension, differs from M in the spectrally flowed sector by the addition of W over 2. Right? That just follows from the spectral flow analysis. But I know already what M is, so now I can write out what this formula is. So what is this formula? You see, this formula will now look like W squared minus 1 over 4W. This is these two pieces together with this. You see, this turns the sign here. Then this becomes W squared minus 1 over 4W. And then I have plus 1n over W plus H rest plus S squared over W.
Sorry, I missed what is H.
So H, that's the eigenvalue of this L0. That's the space-time conformal dimension, right? It's the eigenvalue of that. And because it's J3, but the actual J3 gets shifted by W over 2. So it's not just M, it's M plus W over 2.
Confused, isn't it 1 minus W squared? Whatever, like how do
No, so I add W over 2. So when I add W over 2, then this term becomes a plus, right?
Oh, okay.
Right, so then this is W squared over minus 1 over 4W, and then the rest is just stuff divided by W. Now, so unfortunately, now you should be jumping up and down and saying, wow, but unfortunately you are not, because you are not quite sure what to expect. But to people who know the symmetric orbifold, this is an extremely suggestive formula, because that's basically the conformal dimensions in the symmetric orbifold. So in order to convince you that this is the interesting example, I have to explain to you what we should expect, what we should compare this to. So as I'll explain to you in a second, this is basically the symmetric orbifold spectrum, where this factor is the Casimir energy in the W twisted sector. And this is the excitation numbers, the fractional excitation numbers. That I'm about to explain to you that appear in the symmetric orbifold. So it's a bit hard if you don't know the symmetric orbifold to be excited at this stage, but the moment you see this formula, you realize that you are basically on the right track, because it looks exactly like the conformal dimensions of the symmetric orbifold. So let me explain to you what the symmetric orbifold of T4 is.
Sorry, but what about this H rest?
Right. So this is all take 1, right? So we're going to set this to 0, and then H rest is basically a SU2 factor, and the SU2 factor is a bit delicate here. So we see the gist of the argument, and then we'll do it properly. And when we do it properly, also your problem about the representations will be very clean. There'll be a very clear definition of what the PSU 1,1/2 Westermino-Whitson model has a free field realization. I can be super explicit, so then all of these problems disappear, you only get this representation, and everything will be much cleaner. But the gist of the argument, the fact that you get this structure is basically the same, and it's much more easily to see here than in the more complicated hybrid formalism, which is the reason why I'm explaining it here. Okay, is that sort of the logic clear? So you have to sort of trust me a little bit that while there are details here that are not quite spot on, we are on the right track. Okay.
Just to understand the general goal here, I mean, are we trying to construct, for example, are we going to construct the LNST?
Well, I mean, people have tried to construct that, but that is a bit of a dirty construction. So that is a...
Okay, so we're not, I'm just saying what we are going to do.
At this stage, what we are going to do is we are going to calculate the physical spectrum. And so this is...
say that it coincides with another physical spectrum.
And then you see that this is the physical spectrum of the symmetric orbifold. So that shows that the spectrum matches. And then in the last lecture, I'm going to explain to you that the structure of the correlators matches. Because you can show that they are labeled in terms of covering maps, and you reconstruct this structure from the world sheet.
But they are there somewhere, it's just we don't know what they are.
Yes. I mean, people. So there is this Wakimoto free field realization for SL2R, and in terms of the Wakimoto free field realization, people have written down formally for the Virasoro generators. But these are I mean, when you question whether what I'm doing is mathematically sound, then I would be blown out of this room if I wrote down this formally. So I'm not even trying.
So this spectrum, does it also come with multiplicities?
Absolutely. We reproduce the full Monty on the nose. But only in take 2 it really produces every little detail. Here you just see the gist of it. So trust me, here we're seeing the essential structure, but the details you'll have to wait a little bit. Okay, so what's the symmetric orbifold of T4? Well, so T4 you all know what this is. T4 is basically 4 free bosons and 4 free fermions. So T4 is relatively easy. It's 4 free bosons plus 4 free fermions. So let's say d phi 1 up to 4 and psi 1 up to 4. And now what we are going to do is we are not going to look at 4 fermions and 4 bosons.
D phi?
Say again?
Why you say D phi because it's on a torus, or?
Yeah, it's on a torus. So I mean, So normal. I mean, as you know, the target space fields are a bit awkward. The derivatives of them are good conformal dimension 1 fields, and these are the d phi's. Now, what you're going to do is you're taking n copies of this. Now, in order to explain this, it's a little bit simpler to just look at n copies of S1, because then we'll see the gist of it, and then you just have to take 4 copies in a book you can. And I'm also not going to include the fermions. Let's just look at one boson and copies of it. So here I have a boson d phi, and now
So this n is not the same n as above, or
no, sorry, absolutely, yeah. So this n is the excitation number in the sense of, right?
And that n?
That n is is going to be taken to infinity. That n is to be identified. So this n is to be identified with the string coupling constant. So it's the analog of the rank of SUN. So we are going to take the large n limit of the symmetric orbifold. So we're going to take n, the symmetric orbifold, as I'll explain to you, and then we're going to take the n go to infinity limit, and we're including 1 over n correction.
Is it this dual CFT you're talking about?
Yes, yes. Now we are talking about a dual CFT, absolutely.
Ah, okay.
Right, so you see, here's the spectrum. And now we have to see that this is the spectrum of something we recognize, so I have to explain to you what should you expect. And when I'm saying the dual CFT is that's what you expect, so let me explain to you what you expect if I write down symmetric orbifold of T4. And because it's a bit complicated, let me write down symmetric orbifold of S1, and then you get the gist of it. Okay, so you have n copies, I is equal to 1 to n. And so you don't have one boson, you have n bosons, and then you're going to look at the Fock space, but you're only keeping the terms that are invariant under the permutation action. So obviously you have a permutation action on these. The permutation group just permutes these fields, and what we're going to do, and this is what's called the unfisted vector, you're looking at the Fock space of these d phi i's, and you're only retaining those, probably you want to write this as, I'm retaining only the states that are invariant under the action of the permutation group. Now, in string theory, or in conformal field theory, when you do an orbifold of a CFT, you don't just keep the original theory and keep the states that are invariant under the symmetry. There are new sectors that enter the conformal field theory that weren't there previously. And the intuition is that if you think about considering closed strings, so if you consider closed strings mapping to some manifold, and then now you're dividing this manifold by some group, say the symmetric group, then there are closed strings that were closed before you divided out by the symmetric group. These are what are labeled by the untwisted sector, and those you have to make invariant under the orbifold group. But there are also new closed strings that weren't there before. These are the closed strings that are only closed up to the action of the orbifold action, right? So the endpoints of the strings are really different in the theory S1 to the n, but they only differ by a permutation. And therefore, in the quotient space, this is a new sector of closed strings which you didn't have before. So therefore, in an orbifold theory, in addition to the untwisted sector, which is the stuff that you had before, subject to the constraint that is invariant, you get twisted sectors. And the twisted sectors are basically labeled by group elements. Right? They're labeled by the group element in the orbifold group, telling you how the endpoint, the beginning and the endpoint are related to one another under the action of the orbifold group. Now, obviously the twisted sectors aren't really labeled by all the group elements because you have the invariance condition. So the twisted sectors are labeled by the conjugacy classes of Sn. Right? So you're only keeping track of this modulo conjugation. So the different twisted sectors are labeled by the conjugacy classes of Sn, but we all know what the conjugacy classes of Sn are. These are Young tableaus, right? It's just cycle shapes. Right? So, I mean, you're familiar with this probably. So the most general permutation I can write in this, say, cycle permutation, the cycle decomposition, and then, for example, there will be this cycle and whatever, right? You just write a permutation in terms of cycles, and under conjugation, the shape of the cycles, i.e. the number of cycles with which lengths, obviously doesn't change. You just change the entries inside the cycle. So the twisted sector of this symmetric orbifold will be labeled by all the conjugacy classes of Sn. Now, we are doing string theory rather than string field theory, and as a consequence, we should expect to see from the dual 2D CFT what you would think of as being the single particle spectrum. The multi-particle spectrum of the dual CFT you would expect to come from string field theory, where you have multi-string states rather than single string states. So therefore, what we are going to look at here are what we think of as the single particle states, and single particle simply means single cycle. So we are only going to look at the conjugacy classes that have one cycle of length W and all the other cycles are trivial. And this is to be identified with the single particle state. So in the context of super Young-Mills, these are the single trace states. And as you know, in super Young-Mills you have multi-trace states and you have single trace states. But perturbative string theory will only see the single trace states. The multi-trace states will be the multi-particle string theory states, which you wouldn't see when you do perturbative string theory, because you just have a single cylinder, so you have a single string. So you only see the excitations that correspond to a single string. So we are only going to look at a single particle sector, and in the context of the symmetric orbifold, this means we're looking at a single cycle twisted sectors only. And a single cycle twisted sector will be labeled by one number, W, which is the length of the cycle. Is that clear?
It's the same W or it's a new W?
That's the same, turns out to be the same W, but we don't know yet. Okay, so how do we describe this twisted sector? Well, what does this mean? So what does this mean is, suppose you have a state inside this twisted sector.
Sorry for this critical question, but it looks a bit arbitrary, right? At each point you say you throw away this or that, or...
Well, but I mean, no, it's not. I mean, look, see, if I do string field theory, I'm just going to do the multi-particling, and I'm just going to produce all the other sectors. That's pretty easy to see, that the multi-particle states from the string theory will reproduce the other conjugates.
But still, like the whole procedure, this AdS CFT seems to be at many steps. You need to like guess something.
No, it's not. I mean, that's something people have known long ago. I mean, it's the same with the single trace spectrum of AdS and so on. So this is. I'm just telling you, there is some subtext to the AdS CFT. It's not something we invented. I mean, this is something which.
This is rather established.
This is a well-accepted fact that you're only going to see the single particle spectrum, and the natural guess that a single. I mean, it's almost the only way you can make this work, so that a 1 over n and so on works out, is that this is the single particle spectrum. So this is not something we've added. This is, but there's lots of folklore here. So obviously, I understand when you describe it, this sounds like now I'm invoking yet another trick, but. I'm trying to explain to you, this is not a trick we invented, this is,
no, I don't say it's
a trick that everybody sort of accepted. I mean, just like this statement, I mean, this is something that people knew for long, and I mean, all of these statements are sort of part of the folklore, and we are just using the usual folklore analysis, but we see exactly how it reproduces.
I'm just worried a little bit about something, is that, so this is a very good toy model, it's just that mathematically, right, so the symmetric product of a one-dimensional variety is smooth, and the non-one-dimensional is, of course, that's where there's an orbifold, I suppose. So.
No, even here it's not smooth, right? Because I mean there are fixed points, right? I mean.
Well, actually, it is smooth, but okay.
Yeah, I mean, I think this complication is, you see it exactly the same I mean, S1 to T4, there is no difference. But from a point of view of a variety, it's definitely as fixed points. Right? I mean, these are the,
Yes.
But you know,
Easier, yes.
CFT now is, CFT gives you a very definite prescription for how to resolve these fixed points, which is basically what I'm describing to you here. And there is just a sort of algorithm for what you're meant to do. And what I'm saying is the symmetric orbifold, where you follow the standard algorithm for what you're meant to do, is the theory that matches exactly our worldsheet theory.
Okay.
And that's, I mean, that's what people call the orbifold. So that's, now obviously you can resolve it and so on, but we are sitting at a very specific 2D CFT point, namely the one where you just do the usual symmetric orbifold. You're not doing anything fancy, no funny modifications of what you would normally do. I mean, I think this is a very well studied CFT, this orbifolds and these symmetric orbifolds. I mean, you'll see later. There are many things you can calculate, and it's been tested to death. So this is a very well, very okay. My supervisor, Peter Goddard, he would probably doubt that this is a consistent CFT. But whenever fermions were involved, he was worrying about the signs. Now, I have sort of the next generation. I'm okay with that.
I see.
But if I talk to my string friends, they would say, but this is well known. So this is, so it depends a little bit on where you are on the spectrum of mathematical precision. But I think if you ask the random string theorist on the street, they will say this is.
No, I have nothing against it's perfectly possible. It's just that mathematically, what the procedure you're doing this here in a one-dimensional case, it's much simpler than in the two-dimensional case. That's all.
No, but no, that I doubt. I mean, I think whether I have S1 or T4 doesn't make any difference. What I'm doing here. And I mean, S1 to the n has as many fixed points as, well, has also fixed points, just like T4 to the n. So the difference between
When you pass to the functions and the invariant theory is simpler.
Yeah, but I mean, from the point of view of this, it plays absolutely no role. So what does this mean to have a twisted sector? So what this means is you have your field d phi I, and when you take it once around here, you don't come back to d phi I, you come back to d phi I plus 1. If you are within 1 to w, and then w plus 1 is to be identified with 1, right? So this is what it means to sit in this twisted sector. So now, in order to describe the Fock space that comes from this twisted sector, you have to look at linear combinations of these fields that have a simple monodromy as you take them around the insertion point. So, okay, I'll always get my signs wrong, so let me look at my formulae. So the correct combination to look at is that I'm defining the fields, I mean certain linear combinations, I'm defining d phi L, and d phi L of z is going to be 1 over square root of w times the sum from j is equals to 1 to w, e to the minus 2 pi I Lj over w, d phi j of z, right? So you're just looking at a certain linear combination of them, and then you can convince, it's pretty easy to see that these fields then, when you take them around the twisted sector insertion, will just pick up a phase of e to the 2 pi I L over W, right? I mean, you're just diagonalizing this action, right? I mean, this is not, I mean, for you guys, that's not so
this twisted sector is associated to what? A permutation?
Say again?
Where do you go from I to I plus 1? So sigma is some transposition? Or
Well, sigma is this one here, right? And here I is in 1 to W, with the idea that W plus 1 is to be identified with W.
is the font?
So I mean, yeah.
But it's fine, it's fine.
So this is this W cycle twisted sector, and then the so now when you write down, so these modes pick up this phase, right? So this linear combination picks up this phase. I have a linear combination for L is equal to 0 of 1 up to W, right? I just combine them into W different linear combinations. And then what this means is that if I write d phi L in terms of modes, so I'm going to write down the mode expansion. As you do for fields of conformal dimension 1, then you realize that because this guy picks up this phase, the mode number here is not going to be an integer, but R has to lie in Z minus L over W. Right. So in this W cycle twisted sector, what happens out of the W original fields, you make sort of W new fields, and the W new fields look like a single copy, except that their mode numbers is now fractional. Right? Previously, the mode number of everybody was integer, because they were all single valued. In this W cycle twisted sector, they're not single valued, they pick up these phases, and therefore these guys, well, they pick up these phases, and that translates into the fact that their mode numbers are W fractionally moded. So if you think about it, you see this is exactly what this factor is describing for you. You see the excitation of the boson that you have in the W cycle twisted sector effectively behaves as though that the mode numbers are not integers, but they are fractionally moded in some integer over W, and that's exactly what this factor tells you. This factor tells you that all my excitations I had previously, I have now W fractions of it, and that's exactly what the W cycle twisted sector produces for you. And it doesn't matter whether you do this for S1 or T4 or, right? I mean, this is just totally independent. Now this factor is a little bit more delicate. So how do you understand this factor? Well, in order to understand this factor, you have to discuss the Virasoro algebra. So the Virasoro algebra, so this is the space-time. So I'm discussing the dual CFT, right? So I'm in this world. So the L I'm writing down is the L of the dual CFT. And in the W cycle twisted sector, the Ln will be given by a half times the sum over these funny fractionally moded modes, where sum over all the R. So I'm writing these now as alpha R. And I'm dropping the L index and I'm simply saying, okay, depending on which mode number I'm talking about a specific of these, right? As I run over all the values of L, the mode numbers run over all the fractional numbers in 1 over W. So I can just drop the index L because R knows what L is, because if R is of this form, it's the mode of L, and so on. So I'm just writing it like that. And the Virasoro generators, you can easily see if you're just looking at the modes that come from this W many fields, it's given by that formula. And then you can easily work out the conformal dimension of the ground state, because you see L minus 1 on the ground state in the W cycle twisted sector is non-zero. And it's non-zero because you see some of these modes survive, and now I'm restricting to W odd for simplicity. And for W odd, this is just the sum from L is equal to 1 to W minus 1 over 2, alpha minus 1 plus LW times alpha minus LW acting. So on the W cycle ground state, all the positive modes kill, and all the negative modes create. And now, because they're fractionally moded, there is a non-trivial action of L minus 1, because you see you can choose two negative modes that add up to minus 1, because they don't have to be integers individually, they only have to be W fractionally moded. And I only should include up the sum up to W minus 1 over 2, because otherwise I'm double counting, because they commute with one another. So this is L minus 1 on the ground state, and then you can calculate L1 on L minus 1 on the ground state, just using this formula. And it's easy what you're going to get. You just get the sum from L is equal to 1 to W minus 1 over 2. You basically get 1 minus L over W times L over W. And when you work this out, what you find is that this is W squared minus 1 over 12W. And this is to be identified with 2L0. And therefore you read off that the ground state conformal dimension, H0, is W squared minus 1 over 24W. Right? So this sum here is W squared minus 1 over 12W, but it's equal to 2L0, because this is equal to the commutator, which is 2L0. So L0 is W squared minus 1 over 24W, and that's the correct answer for one boson. But now here, for the symmetric orbifold, you have 4 bosons and 4 fermions, and it goes basically like the central charge. So you have to multiply this result by the central charge of T4, which is 6, and that gives you W squared minus 1 over 4W, and that's exactly this factor. So this factor is exactly the ground state conformal dimension in the twisted sector of the symmetric orbifold of T4, and that exactly looks like the excitation spectrum in the W cycle twisted sector of T4. And okay, so we have here, this is the dirt bit, which we are going to address probably tomorrow. So here you see that things look like they want to be the symmetric orbifold, but I have some problems. I don't quite know why I should restrict myself to the continuous representations, why I should set S equal to 0, all of that. I don't quite know how to deal with the SU2 factor. And all of this will be resolved once I do it more properly tomorrow in terms of the high performance. Yes.
Can you just comment? I'm a little bit lost about the now we have 3 different sets of L's, right?
Yes,
so,
yes.
so what?
Well,
I understood the first 2 how they're different. This third one I'm a bit confused.
The third one is also
Oh, it's the same.
space-time one, but I'm just writing it in terms of symmetric orbifold language.
No, but I mean, are you claiming that those things are the same as these
Yes,
now?
absolutely, yes. So this is, I mean, because I'm claiming that the dual CFT is the symmetric orbifold, and I'm just writing down in terms of the symmetric orbifold language the Virasoro generator, right?
But I mean, you just said the previous times that we don't really know what they are.
Right. I
LS.
don't know what they are from the point of view of the world sheet, but from the point of view of
Just
the symmetric...
constructed them, no?
Well, we
This formula, LMST equals 1/2. What this formula, this in the deconstruction?
That's a construction in the symmetric orbifold of T4, right? I mean, so, right, I have the world sheet theory, and then I have what I claim to be the theory that describes the space-time spectrum. The theory that describes the space-time spectrum, I claim, is the symmetric orbifold of T4. And now I'm just using symmetric orbifold of T4 technology to construct the Virasoro generators. Now, for the symmetric orbifold of T4, I surely know what the stress energy tensor is, and it's basically just the free field version of the stress energy tensor. Now, I don't know what this means from the point of view of the world sheet description. But within the context of the symmetric orbifold, that's a well-defined CFT. I don't know anything about AdS3. I just do my standard symmetric orbifold.
We still get an equality of, I don't know, J something something in this world is equal to
Right,
this.
but that's the dictionary between going from AdS3 to... So here, from here onwards, I've sort of turned the page, and I'm just studying the symmetric orbifold to tell you what you should expect. And in the symmetric orbifold, I know what the Virasoro algebra is, but obviously how it translates to the world sheet, I only know for the 0, plus and minus 1 copy. But in the symmetric orbifold, that's the correct formula, and I'm just calculating. I mean, this is one way of calculating the ground state. You can also calculate by modular invariance. I mean, there's zillions of ways. I thought this is the cleanest way of explaining it to you. So this is, again, a very well-known fact about the symmetric orbifold, and therefore you know that this is the correct formula to expect. And I just wanted to motivate to you that this is the correct formula to expect.
So this T4 and that T4,
Yeah,
they're the same T4?
they're essentially the same. Yeah. But at the moment it's a bit dodgy because we still have this S3 factor, and I haven't yet explained to you what to do with the S3 factor. And the S3 factor, as I explained before, is really now at level -1, so there's some funny business going on. And that is, we haven't got a clean description in terms of this NSR description, but in terms of the hybrid description, this will come out very cleanly. But the sort of structure of how you see the space-time CFT emerging and what you get is essentially the same in the hybrid formalism, but it's a bit technically easier to describe in this context. Okay, so I think I'll stop here. My time is anyway up.
Okay. Thank you. So any other brief questions? Maybe I have one very simplistic question. I really don't understand your calculation here, right? If you have a formula for Lm, why don't you apply m equals 0 and I mean...
Well, okay, so there are plus normal ordering terms, right? Right? But obviously for the -1 mode, the normal ordering terms don't play a role. So in order to, I mean, I could either try to work out the normal ordering terms by solving the Virasoro algebra, but it's safer to just work out L-1. There's no ambiguity about normal ordering. And then I just apply L1. There's again no ambiguity about normal ordering, and then I get the answer, and that must be the correct normal ordering term I should have written.
So that's a very good answer, because on the one hand I caught you on cheating, and on the other hand you gave a satisfactory answer, right?
I'm glad you regard this as a satisfactory answer.
So, any other questions? And Matthias, thanks again. So,